As we continue our discussion of basic TCP/IP, we are going to move into TCP and UDP communications, or essentially layer 4 of the OSI model. What we're going to do is walk through the differences between these two choices that the application has to make when it communicates across the network. Now, you didn't know it when you got into networking, but there is secret handshakes that happen all the time. TCP has one. It's known as the secret TCP three-way handshake. It's how it actually builds its session between the devices that it's communicating with. We'll then take a look in depth at TCP because it is the more complex of the two protocols, TCP and UDP. We'll look at its method of doing sequence numbers and acknowledgments to make sure that data gets there. And then finally, we'll wrap up as we talk about TCP windowing. In the previous video, we talked about IP and how IP addresses allow us to communicate across the network by telling us the original source of who is communicating and the final destination. So for example, down here I have 172.30.5.82. That would be my source in this scenario. And they could send a message down here to 172.30.5.83, which would be our destination. But that is just the IP component. That is just the street address, if you will, of the devices that I'm coming from and communicating to. In this video, we're going to step up a layer and start looking at transport layer communication with TCP/IP. I wanted to review that IP address concept one more time before we got into the new stuff, because I want to make sure I'm hammering home that a network does communicate in layers. At that physical layer, we have those electric signals that are being sent. Move up to the data link layer and you have your physical addresses, your MAC addresses, that allow you to communicate on the local network, meaning a network where everybody's plugged into the same switch. You haven't gone through a router. The IP addressing allows us to communicate from end to end, meaning from an original source to a final destination, no matter how many routers we go through. Those addresses stay the same. Then finally, we move up to what we're going to talk about here, the transport layer. Now I'm working my way up from the bottom of the OSI model, but the way the communication actually works is from its way down. Meaning, without an application sending data, there wouldn't be any network communication to begin with. An application has to communicate across the network, and as that application gets down here to the transport layer, it has to make a choice between two big protocols, TCP and UDP. TCP and UDP is the choice between reliable and unreliable communication. I mentioned this early on when we talked about the OSI model. TCP is the reliable one. It builds connections between the person that it's communicating with. So if a computer wanted to communicate with a web server, it would say, "Hello, web server. My name is such and such, based on the IP address, and I would like to communicate with you." The web server would respond and say, "I see your request. Let's start communicating." And that's considered building a session. Whereas with the UDP side, you notice that we're in a connectionless world, meaning I don't ever introduce myself to the device that I'm sending to. I just say, "Here's the data," and I send it to that destination address. Now that destination address may not even be ready for that packet. It might just get it and go, what's this, and drop it. But we'll never know about it because UDP is completely connectionless. It's just best effort delivery. Moving down to that next item right there. Best effort delivery means you send it, and you sure hope it gets there. It's kind of like the post office. You throw it in the mailbox, you hope it gets there, but you're never really guaranteed. Now, that makes UDP an unreliable protocol. Now you might be thinking, well, why would I use an unreliable connection? Again, I mentioned this back in the OSI model, but to review, unreliable connections are great for traffic that is real time, meaning it needs speed and it's got just a real time feel to it, like voice over IP. When I'm speaking into a phone that communicates across the network, there's no need to resend data that gets dropped along the way because the conversation is progressing. It's not something where I can just back up and resend some dropped words from previously. Online games where you're moving characters around and so on. If you drop a movement, increment, no reason to back up and resend that because the game has progressed. So anything that's real time. TCP, let's come back here, builds those connections. It's reliable. It uses sequence numbers. Now, what does that mean? It means that all of the packets that it sends are tagged with a little sequence number saying this is the 5th packet in the conversation, this is the 6th, this is the 7th, and so on. Because, I mean, think about the internet. When you're thinking of the internet, most people draw it like a cloud, but it's literally millions, potentially even billions of routers that are all tied together with all kinds of different connections. Now, when you're communicating, we'll say from over here at your PC across the internet to some web server, you might have some of the packets that you send take one route and end up there, and some other ones go a different route just because the internet's always changing. It's always shifting what routes are considered best, and sometimes a service provider goes down and everything has to divert. With TCP, with those sequence numbers, the web server can put them all back in order, meaning maybe it gets the 1st, 2nd, and 3rd packet, then it gets the 6th packet, and then, oh, 5th, there's 5th and 4th packet, and then, oh, there's 7. You know, it's kind of getting them out of order, but because TCP has sequence numbers, the server can receive that and go, okay, well, let me just put these all back in order, so when I give them to the computer, it knows how to reassemble all of this data. Last but not least, TCP is reliable. That's the big thing about it. Everything that you send is acknowledged. So when I send something to a web server and I say, transfer that $1,000 to my bank account, the web server has to acknowledge, send an ACK back at me, so my computer knows that it got that transfer. If the ACK does not come, then my computer's going to resend that request to transfer the $1,000 because the web server obviously didn't receive it. And TCP will continue to retransmit those requests until it finally does get there. Now that you've seen the overview of TCP and UDP, let's get into the specifics of how they work. UDP is very simple. Let's say we've got this source host over here, and it's 10.1.1.1, and then I've got my destination server over there, that's 150.1.1.1. With UDP, if I was sending from here to here, I would just send a packet with the destination address on that header of 150.1.1.1. It would be received over here by that server, and the server would just process that data, meaning let me figure out what to do with it. No acknowledgement is sent, nothing verifies that it was received. It's completely unreliable. And that makes sense. That's what UDP was designed to do. But TCP, as I mentioned on the previous slide, starts a conversation. It starts a session with the device that it's communicating with. So it's kind of like, you know, here's a picture to think of. Think of UDP as walking into a room and saying, hello, I would like to give you this Excel spreadsheet, and then turning around and walking out. You don't know if the person was even in the room that was there. You hope they were, and you assume that they were in there to get that Excel spreadsheet, and you just kind of threw it out there, and hopefully they get it. With TCP, it's like making a phone call. If I were to pick up the phone and dial somebody to give them an Excel spreadsheet, the phone would ring and they'd pick up and say hello, and I'd say, hey, it's Jeremy. I just want to give you an Excel spreadsheet. And they go, oh, great. Hear you, Jeremy. Let's go ahead and communicate. You see that there's that session established. The phone call is going through rather than just coming in and yelling and hoping it gets there. Now, the way TCP starts that phone call is through this system known as a three-way handshake. And as you're getting into troubleshooting of networks, and if something's not working, you're trying to figure out what's going on, it's really advantageous to know this process because you can start doing things called packet sniffing, meaning you actually watch the conversation as it happens, and sometimes you may find that there's something going wrong with a three-way handshake. Here's the idea. Again, the computer on the left is the source. When it starts the phone call, it will actually send something known as a SYN packet over to the server that it wants to communicate with. Now, a SYN, it's labeled that because it's short for synchronization. I want to synchronize our conversation. I want to start a conversation with you. Now, the server receives that. It's like a phone ringing, so it picks up and says, oh, you're 10.1.1.1. Let me communicate back with you, and I will send a packet known as a SYN-ACK. meaning SYN, I want to begin a conversation with you. I want to synchronize myself with you. And at the same time, I want to acknowledge, ACK, that I got your SYN packet. Now remember, everything in TCP is reliable. So this one's going to say, got it, and send that right back over. It will acknowledge that SYN ACK packet and just say, got it, now we're good to go. That's why it has the technical name TCP three-way handshake. Every single one of those arrows represents one step in that three-way handshake. After they finish shaking hands, it's like they've answered the phone and now they're going to say, okay, now what did you want? And my server or my client over here would say, give me your web page, and it would send the web page or whatever the case may be. That session is maintained for as long as I am wanting data from that server. Every single time you open a web browser and go to some website, you are doing this process behind the scenes. And it's funny, as we start going through this and we get deeper and deeper in the concept, it's amazing that it happens so fast. But you immediately shake hands with that web server and maintain a session between you two. After the three-way handshake is completed, your computer will begin sending data or receiving data from the server that it's communicating with. Now, as I mentioned, TCP is number 1, reliable, number 2, session-based, and number 3, uses sequence numbers so that it can put stuff back in order. Now, the way the sequence number concept works is like this. We have right here this computer sending some data, and we'll say it decided to tag that with sequence number 10. Now, in reality, these numbers are typically much bigger than just a 10 or a 5 or whatever, but the concept is the same. It's just with a bigger number. So it sends some data, sequence number 10, over to the server. Now, the server receives that and has some data to send back over. So it's going to say, okay, well, I am sending with sequence number 5. You might be wondering, well, where are these numbers coming from? They make it up. The computers just make up a sequence number. Sure, it's more technical than that. Behind the scenes, Windows is managing what was the last sequence number I left off at, what would be a good one to begin at now. And it just maintains all of these sequence numbers behind the scenes. So any given time, your computer might just say, hey, I'm using sequence number 400,372. You know, just some sequence number, and it would shoot across, and this one would say, hey, I'm using sequence number 5,291. So there you have the sequence number concept that just identifies what order this data is in the sequence. So it sends sequence number 10. This one says, oh, I've got some data to send back to you. It will be sequence number 5 is my number that I'm beginning with. This one started with 10. This one started with 5. But look at what's right after it. ACK 11. What that means to this device when it receives an acknowledgement back. Remember, an acknowledgement is there to tell the computer that I received your data. It's good to go. By saying ACK 11, that means I received your sequence number 10, and I am now waiting for number 11. That comes back over, and the computer receives it. It goes, oh, great. He got my number 10, so I will send sequence number 11, and at the same time send an ACK 6, because I want to acknowledge that I got his sequence number 5. See how this is working? Each one of these devices has its own set of sequence numbers that it's using as it's communicating end to end. So the acknowledgments are just acknowledging the data that was sent from the other person. So it's saying, okay, I received 5, I am ready for 6. Comes back over here and it goes, oh, great, you got number 5, so I'll send you number 6. And by the way, I'll send ACK 12, which says I received your sequence number 11. Now, what if something bad happened? Let's say, let me get all my chicken scratch off of here. Let's say that, this device sent sequence number 11 over here. Well, let's not do that. Let's say this device sent sequence number, that's what I said, right? 11. Sequence number 11 over to the other side, but something horrible happened in the middle, and that packet got dropped. What would occur? Well, after a little amount of time, there's a little timer value ticking down in there saying, if I haven't received an acknowledgement from this person in X amount of time, I'm going to resend my data. So when this one doesn't get the acknowledgement back that the left computer received sequence number 5, it will resend sequence number 5 with the same ACK 11. And that tells this computer over on the left-hand side here that they did not, got my pen here, they did not receive my sequence number 11. They must have dropped somewhere in between. So at the same time, I will resend whatever data was in sequence number 11 at that point. Let's move this up a notch. Because this system of sending some data, getting acknowledgement, sending some data, getting acknowledgement, is actually not all that efficient. Because if you think about it, you just send, one sequence group, if you will, of data, one packet to the right-hand side here, and it's going to send an acknowledgement back. Got it. Another one comes across, it's going to send an acknowledgement back. Got it. Another one comes across one at a time, one at a time. It'd be like me talking to you, and you had to acknowledge every word that I'm saying. So I'd say, so, and you would go, got it. What? Got it. Yeah, it would be annoying because we'd have these lag times in between our conversation. So to resolve that, they introduced this concept called TCP windowing. What this does is increase how much data is sent based on how reliable it detects the connection as. So here's the idea. The very first piece of data that it sends just one packet over to the other side and receives that acknowledgement. Got it. So we know that one is good. Okay, life is good. Let's go ahead and step it up. This time I'm going to send 2 packets full of data and receive an acknowledgement back saying, got it. It's going to go, oh, this is nice, and it seems like things are going well. So let me send 4 packets full of data to the other side and receive an acknowledgement back. Got it. That system will keep increasing, actually limitlessly, until it detects that there's some kind of problem. Think of it like throwing baseballs, right? Say you've got a friend standing across the field and you chuck him a baseball and he's like, got it. You see him catch it, you're good to go. And you're like, okay, it was not too bad. You chuck a couple baseballs and he catches one in each hand and he's like, I got it. So you grab 4 baseballs. You're throwing them across the field. These baseballs are whirring and you can see him, starting to juggle over on the left-hand other side, and he's grabbing them and so on. You're like, oh, this is good. So you chuck 8 baseballs at him. All these balls coming through the air, and he catches like the first 4 or 6 of them, and then it's like, the other 2 hit the ground. At that point, you would stop and say, okay, 6 is the maximum that I can send before I overwhelm the other side. That's the same way that TCP windowing works. It's going to keep sending until it realizes that data is getting dropped, meaning the acknowledgement that comes back says, well, I got the first maybe 2 of them. Those are the ones I received. X's aren't the best number, then these 2 are the ones that ended up getting dropped. So it says, okay, well, if you can't handle 4, we'll go ahead and keep our window size at 2, and I'll send you 2 groups of data and receive an acknowledgement back. Sure, as time passes, it's going to try and send a little more here and there just to make sure you can handle it, because maybe at the time the server was bogged down when it dropped those 2 packets, but it eased up a little bit so it can handle a few more, or the network in between was able to handle a little bit more data. That's the concept of TCP windowing. So let's walk through a scenario of TCP windowing using some real sequence numbers and acknowledgement numbers and see what happens here. So what we've got this computer on the left communicating with the server on the right. I'm assuming here that the 3-way handshake already took place. So they have their session set up. So it sends the first chunk of data on over. The server gets it, sequence number 1, and responds with acknowledgement 2. That says, I received 1, I'm ready for 2. At the same time, the computer over on the left says, oh, that went well. Let's try increasing how much I send, increasing my window size. By the way, they call that sliding windows because it slides the window a little bit bigger. So it sends sequence number 2 and 3, shoots over here to the other side. Success. The catcher has caught in the ball. It sends acknowledgement number 4 back saying, I've received 2 and 3. Go ahead and send the next one. So it's like, oh, this is going well. Let's try a little more. I'll send sequence 4, 5, 6, and 7 over to the right-hand side. It responds with acknowledgement number 7. Now, did you catch that? What just happened there? All along, it was acknowledging the next sequence number that it expected. Number 2. Was expected next. Number 4 was expected next. Now it said acknowledge number 7. But wait a sec. I already sent 7. So what the computer assumes as soon as that happens is 7 must not have made it. It must have gotten dropped along the way. So I'll need to resend that and probably back down my window size a little bit because I might be sending too much so that server can't receive it. So it backs it down maybe just to 3 sequence numbers. It says I'll send sequence 7, 8, 9, and it flies across the field and is caught by the server, who responds with acknowledgement number 10 saying, I got those 3. Now go ahead and start your next batch with sequence number 10. Do you see how that works? Now, in the real world, in real numbers, I should say, this is exactly what happens. Don't let me lead you astray in saying, oh, this isn't how it is in the real world. But the numbers are just much bigger because the sequence numbers actually reflect how many bytes the computer is sending at once. Now, when computers handle size, you know, a byte is essentially one character, one byte. So it might send maybe 100 bytes. So sequence number 100, if we started from 0 or started from 1 and went up to 100, sequence number 100, 100 bytes of data would be sent, and it would send back 101. It's like, oh, that's great. Let's go ahead and try sending 200 bytes of data. This comes across and sends acknowledgement 201. So it's like, oh, this is great. Let's go to 400 bytes of data. It actually increases this exponentially to try and get this fast window size. Here's something you may have seen. Have you ever been in Windows and you drag and drop a file over to copy across the network, and a window pops up right away and it says, I'm copying the file. It will take 3 hours left. And you're like, what? That's a long time. And then you wait a couple seconds. It's like, oh, nope, just kidding. I can do that in an hour. You're like, oh, okay, that's better, but still a long time. Wait a couple more seconds. It's like, nope, nope, I can do that in 20 minutes. And you're like, what is Windows doing? Doesn't it know how long it's going to take to do this? Well, what's happening behind the scenes is if it used a sequence number of, we'll say 100 bytes at a time for every acknowledgement, then it would take 3 hours to send it because it'd have to wait for all these acknowledgments to come back and so on. But as it increases its window size, it's able to say, well, if I can keep this window size, I can make this happen in 20 minutes. If I can keep this one, you know, as it grows bigger, it can do it in 10 minutes. So that's that time estimate that you see when you copy a file in Windows is actually reflecting the concept of TCP windowing behind the scenes. Excellent. I love moving up in the layers of the OSI model because it becomes more and more real as you get into the upper layers of communication, especially the transport layer. And don't worry, we're not done with the transport layer yet. This is just one half of the transport layer. In the next video, we'll get into the other half, or as Paul Harvey would say, the rest of the story. So we saw, as we walked through this, the difference between TCP and UDP, and it is a big one. TCP being your reliable method of communication, UDP just sending it in hopes that it gets there. We saw the TCP three-way secret handshake that allows the session to establish. Then we saw the sequence numbers and acknowledgments that allow you to keep all the data in order between end to end and make sure that the data got there as it requests the next section. Finally, we saw TCP windowing, which allows you to be more efficient when you send, so you don't just have to send one packet and get an acknowledgement and kind of wait while all that's happening. It allows your network to communicate much faster. I hope this has been informative for you, and I'd like to thank you for viewing.